All right, so it's 3.5 is the average value. Should also be able to tell what alpha 1 is. If you really know, so average value of x of t is 3.5. That's alpha 0. Alpha 1, how can you tell what that is? How do the alpha values relate to the sine wave that's there? What's that? No. I mean, what do the alpha values tell me? Hopefully you know. What do the alpha values tell me? What do they tell me? I know you guys have some idea. You should. Well, then I should give you even a lower score on the exam than you earned, right? What are the alpha values? What do they mean? Yeah, they're so magnitude. Okay, so the alpha values relate to the individual harmonics. The magnitude of the alpha values tells me something about the magnitude of what? The magnitude of the alpha values tells me something about what? All right, it's Fourier series. Fourier series means the periodic waveform is a sum of sine waves, right? So the alpha values relate to the amplitude and the phase of the sine waves, right? So alpha 1, what harmonic am I talking about there? First harmonic. So the magnitude of alpha 1, how does it relate to the sign that I have there? Well, so it's whatever the amplitude of this thing is divided by 2. 2 times the magnitude of alpha 1 would be the amplitude of the term. Yeah. Yeah. So you guys know. You know, I have to shake the cobwebs the right way to make it make sense. Okay. All right. So the magnitude of alpha 1 is equal to C1 divided by 2. So looking at this, what's the amplitude of that sine wave? The amplitude's not maximum value is 7. The maximum value is, yeah, so the amplitude is 3/2. So this guy is 3.5 divided by 2. All right, or what's that? 1.75, I think. All right, is what that's going to be. All right, so if I calculate these two integrals, that's what I would get, right? So I chose something what you guys can just sort of see by inspection. Now the question would be, all right, so what happens if I were to try to do that back to the definition of an integral, all right? Which, let's say I have just a very simple function, x of t, and I was trying to compute the integral from 0 to t, x of t dt. All right, now you learned the definition of an, what is the definition of an integral? Area under the curve, right? So what was the way that they kind of introduced that? Yeah, so what the heck is that? It's an approximation. It's an approximation. All right, so basically there's a couple of ways. I'm not sure about the Legos piece. What'd you guys say? Somebody say Legos? All right. Basically what I say is I can think of this thing as being sort of a bunch of little triangles or rectangles, right? Where I take the area of each of those rectangles and keep summing that up. All right, so there's a couple of different ways I can do this, but I'm going to call this point here, I'm going to call this time delta t. I'm going to call this 2 delta t. I'll call this 3 delta t. I'll call this 4 delta t. 4 delta t, like that. All right. So those are rectangles. So how do I compute the area of those rectangles? So the idea of the integral basically is you say so approximately, right? I would say some sort of summation down here, right? So what I want to figure out is what am I summing? Without go through the math too formally right there. Basically what you're saying is I've got all these rectangles, right? And I take the area of each of those rectangles, and then what would I do with the delta t values? What should I, so the delta t, if I really get to an integral, what do I do with the delta t? So delta t is the width of those rectangles, right? So what's the width of the rectangles? I let it get smaller and smaller. I take the limit as delta t goes to 0. That will get me to what the true integral really is. All right. But if I choose my delta t small enough, I should just be able to use a bunch of rectangles. Right. Now, how would I do that here? Well, let's say I wanted to take the area of this first rectangle here. First rectangle actually has a height of 0. The way I've drawn it here is starting right here. All right. And so I would say I have x of 0 times delta t. That's the area of that first rectangle. What would be the area of the next rectangle? Well, I said this time right here is delta t. So I would take x of delta t times what? Times height times width, right? Area. Height times width, right? So I'd say x of delta t times delta t, right? What would be the area of the next rectangle? Yeah, x of 2 delta t times the width, which is delta t, right? The width isn't getting any bigger, so it's the width is delta t each time, and then I keep going, right? So I say x of 3 delta t times delta t. Now there's all kinds of ways to write the sum, actually, right? So I did this using through the left-sided approximation. I could, there's a couple of ways that you could set up the box, right? But yeah, and we don't need to get into all the details of that, but do you guys agree that that makes sense? All right. Jonah? You're making hand gestures like, okay. All right. Well, so if I think about how would I set up this type of a sum? How would I set this up? If I wanted to compute the area from 0 to some time in the future, how would I set this up? If I wanted to compute this integral. So this guy here is the integral. This guy would keep going, right, until I get to the endpoint, right? So how would I set that up? How would I set that kind of a summation up? What looks like a natural way to go through this? For loop, right? But basically, if I have an x vector of some kind, like I have here, I would kind of loop through that x vector. Okay, so let's think about that for a second. So I have an x of t, right? Let's say I've been given that x of t. I would have to compute a delta of t, right, to be some number. Okay, so how would I set up a for loop to do that? Right? How would I set up a for loop to do that? For well, so let's think about it. If I'm gonna and let's say I'm going like this, and let's say the way let's set this up. So the waveform that I had here was I had x of t equal to 3.5 plus 3.5 sine of omega naught t. All right. And let's say the way that I set this up in my code is I define my t, which was 1 over 180 in this case. That's the way I defined it. All right. So let's say I did my delta t. I'll write it over here. My delta t was, let's say, t divided by 1,000. Okay. Let's say that's the way it's been defined. Okay. There's a time vector that was defined 0 in steps of delta t. And for this particular waveform, I think I did this over 1 period, 2 periods, 3 periods. Okay. So I defined this time vector for 3 time periods. Okay. All right. So I have an X vector. I have a delta T that I've defined. And I want to compute the integral. All right. And I specifically wanted to compute the integral over 1 period. All right. Over 1 period. So how would I set up the for loop? First of all, what should come out of my for loop? A number, a single number, right? Because I'm trying to compute the area under the curve, which should just be one simple number. Okay. So I'm going to call that guy alpha 0. All right. So let me alpha underscore 0. And I'm going to initialize it, right? What should I initialize it to? Well, that would be the end. I can initialize it to 0, right? Because I'm going to have it compute it for me. Now, hopefully it should come out to 3.5, right? I could set it to 3.5 because I can see it, I guess, right? And then not do the for loop, right? But let's see if it'll work. So alpha 0 will be equal to 0. So how should I set this up now? So I'm gonna use n as my index, right? And I'm gonna start at index 1. I'm gonna do it in increments of 1. And if I want to do this over a period, given the way I've defined everything, how many points should I loop over? Over to 1 period, yeah? So that would be 1,000 points. Okay, so 1 period. And how would I then set up the calculation for the integral? Right, so we said basically every time I go into the loop, I take out the value of x and multiply it by delta t, right? And what else do I do? I add it to whatever I've accumulated up until then, right? So the first time I come in here, alpha 0 is equal to 0, okay? So alpha 0 would be equal to what? Since I'm accumulating, how do I set up a code where I'm accumulating like that? Well, first of all, all right, let's do it this way. How do I compute? So what I'm doing is I'm adding every time I go through the loop, I'm adding a new value in. And the new value I'm adding in is basically, it looks like it would be the current value of x times delta t, right? So how would I do that part? How would I do that part? That would be x of what times what? X of n, the current value of x, right? Times what? Times delta of t. Delta t. All right. Now that's just going to give me the area of one rectangle, right? But I have to add that to the area that I've computed up till then. So how do I include that? Well, what would I be concatenating, right? Because if I do a concatenation, what's concatenate mean? It's a big word, right? What's it mean to concatenate? It means to add something. It means to basically put two vectors together, right? So I'm basically making a vector longer. Now, am I doing a vector in this case? No, I'm doing a sum, right? So instead of concatenating, right, what would I be doing? I'd be adding this value to what? So the thing that we're computing at the end of the day is alpha underscore 0. Alpha underscore 0 is my integral, right? So let's just bear in mind alpha 0 is the integral 1 over t, 0 to t, x of t dt. So that's going to be, the integral is just one number because it's a definite integral, right? So where's the result getting stored every time I go through this thing? Alpha 0, right? So I'm going to add it to whatever alpha 0 is. Right? So alpha 0, then that's calculus, right? I mean, honestly, that's probably a lot more useful than calculus itself. I shouldn't record that and put that online, but if you think about it, right, knowing the closed form solution to all the calculus isn't as useful as understanding that it's an area under a curve and actually computing this, right? All right, so let's look at the code. I wrote here. All right. So I said the frequency is 180, T is 1 over F, omega is 2 pi over T. I defined my delta of T, defined alpha 0. I also did alpha 1 here, all right, which we're going to get to in a minute. All right. So here's that line of code. What's this thing I got down here at the bottom? Alpha 0 equals alpha 0 over T. Why did I put that here? Well, I'm not dividing it by the number of steps, right? Basically, what am I doing in this line here? What's that? Well, let's look at, I'm trying to compute the average value, right? So the average value is 1 over T times the integral, right? So the 1 over T is the fact that so I'm bringing the 1 over T in at the end, right? So I could have, if I wanted to, I guess, included that in this multiplication, right? So I could have included it there, but all right. So we all agree that the answer should be 3.5. All right, so let's run this here real quick. The answer should be 3.5. Let's see what it tells me. If I go to the command prompt, alpha 0 is 3.5. All right, exactly what we wanted it to be. All right, now, the other thing that I wanted to compute was I wanted to compute alpha 1. All right, now let's remember, alpha 1, we said was 1 over T, integral 0 to T, x of T, times e to the negative j omega naught T dt. All right, we said that was our own. Again, it should be one number. In this case, the number is going to be complex, right? And in fact, well, let's get that in a second. We said that the magnitude of alpha 1 should be equal to 1.75. All right. So how do I code that in there? How would I modify this code to get that alpha 1? So first of all, I got to create an alpha 1 variable, right? And what do I initialize it to? 0. All right. So alpha 1 equals 0. All right. Now, how would I code in this? So what's my, first of all, what's my integrand here? That's the function I'm integrating. That's my integrand, right? So the height of each box is different. So basically what we did here is I was taking the integral of x of t dt, right? So I was taking the height is the value of x of t, and the width is delta t. So in this case, what's the height of the function? It's not x of t, right? It's that whole thing, right? X of t times e to the negative j omega naught t. So I would basically now put in here alpha 1 is equal to x of n times what? Yeah, exponential negative j times omega times what? Not t. T is a vector, right? So I'd have to say t of n to get that specific point out of it, right? And then I would have to add that to alpha of 1 because I'm accumulating. I guess the right term, like concatenation, is where I put two vectors together, right? This would be I'm accumulating, right? Sometimes that's what we call this, is an accumulator. You're adding values onto it. All right, that's a common term to use in coding, particularly in controls coding, right? Where I use summations like this a lot. All right. Now, what am I going to get for that? I should get that the magnitude is 1.75. Well, what's the angle going to be? This is probably a little bit trickier. Because this is a sine function, what should it be? So the angle of alpha 1 is what? So it's the angle of the equivalent cosine. All right, so if I had sine of omega naught t, what's the equivalent cosine angle? Negative 90 degrees, that's right. All right, so that means that I should get that alpha 1 is 1.75 times minus j, right? When I do the calculation, because it's going to give me a number in rectangular form, right? So, all right, let's look at my code again. All right, here's my code. So I calculated my alpha 1. Alpha 1 equals x of n plus exponential blah, blah, blah times delta t, right? So, and then at the end, I have this 1 over t again. So I'm going to do this whole thing here. And I get that. Let's see what it comes out to be. All right, alpha 1 is 0 minus 1.75 times I, right? It's exactly what we would sort of expect it to be. So that's the basic approach to doing numeric integration. Now you could there's all sorts of ways to do numeric integration. You can use trapezoidal rules and Simpson's rule. There's all kinds of rules that you can do, right? But this one works well enough. Okay. Now you have I think it's in problem 2. If you've looked at problem 2, let me see if I've got Canvas open. I probably have Canvas open, but it's probably got to refresh itself. Yeah, let's see. Let's see. Oh, it is open. All right. So where are you going to use this? You can use this in an ugly function, probably. You would have liked to have used that probably on the test the other day, right? That would have been a lot easier probably than problem 1 that I gave you. I think you guys froze up on figuring out the equation of a line. I had to make sure you were awake on that one, yeah. So you gotta do it here with this guy. Now this is, this is really kind of tricky to see this right here. At least you want to download and look at the PDF. It should be a lot clearer. What I ask you to do is you actually have to use the sawtooth function in MATLAB, right, to create this waveform. And then you have to do the integration numerically. Now I tell you what your time step should be, delta t over 10,000, right? So, and I tell you to basically you would create it from here to here, right? So you'd create 10,000 points and you do your integration that way. And I tell you to ultimately figure out what the Cn value is for n equal 1, 2, and 3. So you would basically just do what we just did, the alpha calculation, right? For -3, -2, -1, and for 0. But the 0 one should be pretty obvious. Again, if you look at the actual PDF, if you download the PDF, it'll be a lot clearer, right? And you'll be able to see it a lot better than you can here. I've seen it in the real PDF. The real PDF is a lot clearer. All right. The other thing, you can barely see it here, but there is this times 10 to the minus something that is multiplying all of these values here. All right, so you'll need to take a look at that. Again, it's a lot clearer in the real PDF. Okay. In this viewer, it looks a little bit funny. Okay. All right. All right. That's numeric integration. That's hopefully a fairly straightforward point. Okay. Questions about that? All right. Problem 3 asks you to do that as well. Problem 3, I gave you a waveform. You download that waveform and you go and compute those numeric integrals. Well, so there is an audio signal. So problem 4. All right. No Star Wars on this one. Yeah. Yeah.
Audio signal.
All right. No, we can talk about Monty Python and the Holy Grail later. I am not a fan of that. So no, let's not go there. Yeah. So basically what you're doing is something that you're familiar with. I mentioned this once before. So you're doing a touch tone decoder. All right. So basically every time you press a number, so how does it know? Like, oh, press 1 for English, press 2 for Espanol, right? How does it know that? Basically, there is a series of 2 frequencies that are played together when you do that. All right. In other words, for each row in the number pad, And each column in the number pad, there's a frequency associated with it. Okay. So apparently 697 hertz is the top row, and 1209 hertz is the first column. So if you press the number 1, right, what you get is the summation of two frequencies. So let's look at number 1. I got 697 and 1209. So what do you, so basically what you have to do is this is where you would use the Fourier transform. All right. So what you do is it picks up. So digit 1, I'm going to say D1 of t is equal to sine of 2 pi 697t plus sine of 2 pi 1209t, like that. All right. So that waveform is what is picked up, and it basically takes a Fourier transform of that thing to figure out what signal it is. All right. So it basically just it records the audio and then figures out what's there. So if I see this properly, right, what should the Fourier transform, if I looked at the magnitude of that, so that would be the magnitude d1 of omega, right? What should that look like? Should have delta functions where one of them will be at 2 pi 697, and there should be one at 2 pi 1209, and here at the negative values. All right, so negative 2 pi 697 and negative 2 pi 1209. So basically, if you want to figure out what digit's being pressed, what it does is it basically has a system where it's going to say, all right, it hears some unknown signal, x of t, right? It hears that and then basically converts it into, there'd be an analog to digital converter. Okay. Then what it does is it basically says it runs some code. The code is going to take the Fourier transform, and then it's going to look for the locations of the peaks. Based on the locations of the peaks, it's going to be able to say, okay, that was the number 1, or that was the number 2. All right. And if you fat finger it and press 1 and 2 together or something like that, it's going to see 4 peaks, and it's going to know, oh, that was bad. So go back to the beginning, right? All right. So the problem that you have there is I basically uploaded so I have you mess around with this, and there's some code that you got to write to do it. Then what you download is a phone number, basically, right? Which is it's basically a series of number presses, and you have to decode what the number is. Whose phone number is not mine? Yeah. What's that? You can try calling it, but I don't know that it would mean anything. Right. Yeah. Yeah. All right. So question we got to figure out real quick though is, because this is coming into a computer, I have x of t is what I have over here, and then what I really end up with over here is x of n, right? I just get a series of samples, right? And I wanted to introduce that concept. You need this on the last problem, right? So in other words, it's what I would call a discrete time signal. So let's look at this. If I have, let's say I have x of t equals cosine 2 pi 100t. Okay. Now, when you create the time vector to plot this sort of thing, you always end up saying you choose a delta t value, which is equal to, I don't know. Usually I end up doing something like the period divided by 1,000 or something like that, right? So if I said t divided by 1,000, okay. Another way of looking at this is to say that I can think of this as x of n, all right? Where if you think about the time vector, what would the time vector look like? The time vector would be 0, and what would be, let's just write it out. So if I do my delta t like that, the first entry would be 0. What's the second entry? Wouldn't it be delta t divided by 1,000? Or sorry, t divided by 1,000. What would be the next one? What's the next time? If my increment is delta is t the period over 1,000, what would be, so the first value is 0. The next value is t over 1,000. What's the next one? Well, okay, so let's look at it this way. When you guys write this out like that, right? MATLAB populates that vector. It's going to have 1,001 points. Okay. So t, if I exploded that vector to see what was in it, the first entry would be 0. What would be the second entry? T over 1,000. What would be the next entry? 2t over 1,000. That's right. And then the next one would be what? 3t over 1,000. And I basically keep going until I get to basically 1,000 t over 1,000, right? Okay. So if I look at the nth entry in that thing, right? What do I have? Like in general, what's the nth entry there? So t of n, yeah, basically is n times t over 1,000, or n times delta t, right? So I could think of this vector that way too, and I could say it's like I have x of n is equal to cosine of 2 pi 100 times t over 1,000 times n, like that. Now what I've done is I've removed time from that thing, and that's really kind of the way it is. If you think about it, what you have is, yeah, it's discretized now. I've basically got this as just a series of numbers in the computer. Now what that means is that this thing comes out to be a little bit funny in terms of the actual frequencies that I've got. All right. It's not that big of a deal, and it's easy to fix. All right. So I end up with, all right, so I got x of t was cosine 2 pi 100 t, and I had x of n equal to cosine 2 pi 100 times t over 1,000 times n. Okay, so that was what I had. Now the other thing, this value right here, we called this delta t. Right? Delta t was t over 1,000, and again, nothing special about t over 1,000. Nothing particularly special about it, right? I could choose all sorts of different numbers for what that spacing is. The other thing that I sometimes call this is I relate this to a frequency, and I sometimes write this as 1 over f sub s, where f sub s is equal to what I call the sampling frequency. All right. So sampling frequency means how fast did I sample the waveform. In other words, I get samples. If I look at what comes out of the analog to digital converter, I get what I call samples, right? I get basically numbers that were peeled off of the curve. Okay. And so what I end up with is a set of samples that I read off the curve at a particular rate. You know, it's often the case. I've talked about this all in terms of this delta t. How big was the time between those samples? But that's typically a really small number. It's like a 10 to the negative 5th or 10 to the negative 4th or something like that. We usually tend to write this thing as a frequency, right? So if delta t was equal to, let's say, 10 to the minus 4th, what is the sampling frequency then? 10 to the 4 or 10 kilohertz, right? Now, on the problem that you have, it is a very common audio number, 8,192 hertz. All right. In the audio world, that there's a specific set of numbers that they often use. So 8.192 kilohertz is the value that you have. Now you use this in project 1, right? In project 1, I think I may have let me see, I might be in the right directory here. Let's see if I am. Yep. All right. So if I do x1 is the vector that I tell you to use, and I tell you to use that sound command again, right? And you have to tell it the sampling frequency. In other words, how fast does it actually play the samples out? Now, it's faster than you could obviously type that, right? But you can still process that. All right. The way I tell you specifically how the digits are spaced out in that file, so you don't need to worry about splitting it up. All right. So that's the basic idea. Now the thing is, you will need to understand this to go through this problem. So we're going to talk about this a little bit more next Monday. But basically, what I see here is, I found out that this x of n was cosine 2 pi f divided by fs times n. All right. Now, what that means is that the frequencies in discrete time, this is what I call the discrete time frequency. Now, for reasons that you're going to learn more about later on, not in this class, f sub s, what's the maximum value you could ever really have? Well, if I'm trying to sample a cosine, there's a particular maximum value. So really, f sub s equal to f is kind of the fastest you could ever really have. All right. Actually, f sub s equal to f over 2 is the fastest you could ever have. All right. That means that the frequencies in discrete time are going to be between 0 and what number? So maximum value is f over 2. Be 0 and pi. All right. Would be the maximum values that I could ever end up having. Okay. Sorry, not f over 2, 2f. All right. Again, that's not all that particularly important. The thing that you have to be able to do is you're going to have to figure out how to translate those frequencies into discrete time frequencies. But that's pretty easy, because I tell you that f sub s is 8192, and I tell you what all the values of f are, right? So for 697 hertz, it's 2 pi times 697 divided by f sub s, right? That's one of the discrete time frequencies. All right, so it's pretty straightforward to figure out how to do that conversion. The harder part is where you're going to, and it's actually not that hard, right? But you're going to have to write the Fourier transform out. You're going to have to do code to compute the Fourier transform. So that part we're going to talk about, basically, how do I compute x of omega for an input x of t? All right, so we're going to talk about that next Monday, but basically it's pretty straightforward. I basically give you a set of code and I say, all right, I start at the first entry and I go to some particular point. All right. And it's some free, I don't know. So I don't want to, I'm going to write it wrong if I write it off the top of my head. All right. I should know how to do it, but it's something basically like this. What I have here, we're going to do an example of this. I was planning to do this next Monday, but basically this is the only part you probably wouldn't be able to figure out over the break if you wanted to get into it. But if over the break you work on this and you get through problems 1 through 3, good for you. All right, you're pretty much done. I have my feeling is that you won't. All right. Yeah. All right, you'll be enjoying your turkey and such. Yeah. Yeah, that's my feeling. Anyway, so I'm going to stop there, but I'll post this for those of you that do